Okay, as far as the webinar itself, the title, as I mentioned, is Introduction to 4-Axis Machining. We'll start with what is defining 4-axis milling. What is 4-axis milling? We'll talk a little bit about the part orientation and setup that's required for you to do 4-axis milling in our product. We'll also talk about the machining workflow, the actual machining workflow that most parts will have to go through in order for you to be successful with the programming. Then we'll talk about common machining strategies, and that's bifurcated into two segments. One is called index machining, and where we'll be actually showing 2.5 axis and 3-axis methods, how you can employ them in a 4-axis machine using 4-axis index machining. And then we'll jump into the continuous machining, where again, there are two different types of continuous machinings in our system. One is called the wrap methods, where we are basically taking 2.5 axis facing, pocketing, and profiling tool pads and wrapping it onto a rotary cylinder or a rotary axis to give you a 4-axis continuous machining. This in effect is actually taking one axis, either X or the Y, of the 2.5 axis machining method and converting that to a rotary axis. So it's in reality it's really 3 axis, but on your machine it is continuous 4-axis machining. And then we'll also talk about projection methods, where we're talking about parallel finishing, engraving, and engraving. We'll do this in the introductory. There's other methods that we'll go into in the next webinar, but we'll start out with the parallel finishing and engraving for this webinar. And then finally, we'll show you how to post-process these toolpaths. All right, Uday, without any further ado, it's all yours now.
Thank you, Joe. Hello, everyone, and thank you again for joining us for our AMS webinar series. Today, we will be covering 4-axis machining, and we will be, taking a look at the basics of 4-axis machining and how we will, effectively be able to program parts using 4-axis machining. Now, the 4-axis machining is available in our mill module, starting with expert configuration and above. So if you're using expert, professional, or premium configuration, you will have access to 4-axis. Now, in the first example, I will be covering indexed 4-axis machining. Now, before I get into indexed 4-axis machining, we will first learn about what is 4-axis and how we are going to basically orient the part, set it up, and then we'll talk about the machining workflow, and then we will jump into programming some parts. Now, 4-axis, also known as multi-axis machining, is used for programming parts that require machining from one or more orientations. So considering a part has features that needs to be machined from the top, from the sides, from the bottom, you would need to machine this in a rotary axis, where the part is typically held on a rotary chuck and it can rotate along the rotational axis, or so the axis of rotation for 4-axis can be defined about either x-axis or y-axis. So this information can be input based on your machine configuration in the machine tool setup dialog, where you can specify the number of axes to 4, and this would be a table configuration where the part will be rotating about your rotational axis, which could be defined either along X or along Y. So in addition to your 2 or 3 linear axis, a 4-axis is also involve a rotational axis. The rotational axis could be defined as an A axis or a B axis, or whatever the axis code your machine tool expects that can be configured in the post, and the rotation will be typically output in degrees. So you will have 2 linear axes, which could be in translated in inches or millimeter units, and then your rotational will be output in degrees when we program 4-axis or multi-axis toolpath. So typically in most of the cases it would be two linear and a rotational axis when you program continuous. We also have a true four-axis method, which we'll be covering down in one of the other webinars, where you can have all three linear axis and the rotational axis, so which makes it up to a full four-axis or a true four-axis machining. So the four-axis methods that we're going to be talking about here will involve using a rotary table where the part is being rotated on a rotational axis on your machine, or which can be held with a rotary chuck and a tailstock, or it could be however it's being held on the machine. So the part is able to rotate and the tool will remain normal or perpendicular to your axis of rotation. Now, the next thing we want to talk about is how do we orient a part for programming in four-axis. So the first step here is we need to determine the rotational axis. That's how it is set up on the machine. On most CNC mills, the rotation axis would be aligned or rotating parallel to your x-axis. So you need to make sure that the part is oriented and about the x-axis, and you want to establish the origin accordingly. So in this particular example, I'm going to be orienting the part about x-axis on the four-axis setup. The first step is we go into the Program tab in the mill browser. So if you do not have the mill browser or the machining browser open, you go up to the CAM menu and then select Mill to load the mill browser. And under the Program tab, we would go to Machine, and then under Number of Axis, we would pick 4, and the configuration would be Table, since the part is going to be rotated on a rotational axis. And in the next step, we would define the rotary axis about which the part is going to be rotating. So if the rotary axis on the machine is along X, you would pick X positive or X negative. So the X positive or X negative depends on which way the rotary axis is set up on your machine. If it is mounted over to the left side, and as you see, the direction arrow for the rotation axis is pointed by this green arrow. So your rotation follows a right-hand thumb rule. So as you roll your wrist towards you, this would result in a positive rotation angle. As you roll your wrist away from you, would resulting in a negative angle. So you could choose, depending on which way the rotation is performed on your machine, you could choose between positive X or negative X for your rotary axis. Most machines, it could be positive X, and in this example, we'll pick positive X. Now, if your rotational axis on the CNC machine is oriented along the Y-axis, we would pick Y, and we may also have to rotate the part to orient it along the Y. We will be covering that in another example. So for this particular example, we're going to pick the rotational axis as X. The rotary axis limits, I'm going to set it to no limits, as most machines can handle any rotational angle, like going from plus or minus infinite, or there's no real limit on restricting. Or if you need to limit it, you can choose from one of these options, or you can even use a user-defined limits. So once these settings are specified, we'll pick OK to accept it. In the next step, we need to go ahead and establish the location of the origin for machining. And we will also define our stock. So for this step, we're going to go ahead and specify the stock first. I'm going to use stock. I'll pick a box stock, and I will go ahead and set the stock to copy the model bounding box. So the length of the part is 8 inches, the width is 3, and the height is 2 inches. I'll accept that. And I would like to place the origin, the XYZ origin. I could set it to one of the corners of the block and the top in the Z axis. So I would do align, set world coordinates, set to stock, higher Z, and I'll pick the southwest corner. And I'll select OK to accept it. So this will automatically translate the part and the stock to the origin. Now, in four-axis setups, one of the key things is establishing the rotation center correctly. So I'm going to go back to the machine setup dialog and make sure the rotation center or the rotary center is set to the center of the block in here. So that's the center about which the part would rotate. Now, if you're setting the 0 to the top of your workpiece or the stock, then you want to make sure the rotation and center is being set to the center of the block. So in this case, it's going to be half the distance on the Y, which is going to be half of 3 inches. So that would be 1.5 inches. And the height would be, the center and the Z would be half of the 2-inch block height, which would be 1. So that would be -1. So that would be putting it right in the center. Now, if you're setting the 0 right to the center over here, then you can leave the rotation center at 0, 0, 0. So in this case, as we are setting the 0 to the top of the stock material and to one of the corners, we will need to make sure the rotation center is being set to the center of the block. I'm going to select OK to accept this. So now we have the origin set to the top, the work coordinate origin, which could also be like your work 0. And we have the rotation center set right to the center. So if you take a look at it from the top view or from the front view, you will notice that the rotary center is set to the center of the workpiece. So now that we have established the machine and we've set up the origin, the next step is to go through the programming workflow. So we will pick the post processor, the machine tool that you're going to be generating the output for. The posts that are included in our library here, standard library, most of these posts are already set up for 4-axis. And if they're not set up, we can always help you update your post to define the rotational axis code and make necessary changes to the post processor. So I'm going to use, in this particular example, I'll pick Mach 3 as the post processor and set the posted file extension to NC and accept it. Now the machining workflow is going to be very typical to what we've noticed in our 2 and 3 axis machining strategies, where you basically load the part and your stock, and then you could create operations, roughing operations. This could be using a combination of 2-axis or 3-axis operation, where you could be programming facing, pocketing, or 3-axis roughing operations, and then generate pre-finishing and finishing operations, which could be using profiling, engraving, hole profiling, hole pocketing, and then you simulate the operations to verify, make sure the cut material simulation looks correct, and then you would finally output the toolpaths that you programmed out to your machine tool. So we're going to be following a similar machining workflow in here when we program this part using indexed machining or continuous machining toolpaths in our 4-axis machining demonstration today. So now that we have oriented the part, we have oriented the established the coordinate system for machining, and we have specified the rotation center and defined the machine configurations 4-axis. The next step is to determine the best programming method for programming a part like this. Now, since this part is prismatic and we have features that needs to be machined from different orientations. As you take a look at it, you have a pocket that's on the top with some holes, and then on each of the sides we have counterbores and holes that needs to be machined. Now parts like these can be efficiently programmed using index machining, where you lock the rotation to one of these angles, like could be 0, 90, 180, 270. So any of these orientations, and you can program 2 and 3 axis operations. So this method of programming by locking the rotational axis to an orientation along the axis of rotation and programming is known as indexed machining. And you could use the available 2 and 3 axis methods that is offered to you in your configuration. So if you're using expert configuration, you will be able to use your existing 2 and 3 axis methods with index 4 axis. If you have the professional or the premium configuration, you can use your 2-axis and all of the advanced 3-axis methods that are available to you as part of index 4-axis machining. So the first step here is I would like to program the features that are here at the top face of the part. So this would be very similar to how you would program your 2-axis operation. So the Z-axis is normal to the top face. So I'm going to go ahead and create a few machining operations in here. So we'll start with a pocketing operation. So we'll go into 2-axis I'm going to pick pocketing and select the features for pocketing. I can use select curve edge regions, or I can use select surface boundary. I'm going to pick this floor of the pocket. I can do that, or I can say select curve edge regions and use the chain command in Rhino to pick a chain so it auto chains the face edges. The next step, specify a tool, set my feed speeds, set the clearance. Over in the cutting parameters, you can specify your tolerances, stock to leave. You could choose your cut direction, step over. Under cut levels, since I chose the floor of the pocket, I'm going to pick location of cut geometries at bottom, and then I will measure the total depth by picking 2 points, one at the top edge, one at the floor. That's a 1/2 inch deep. I would like to split it in 2 levels. Specify the entry and exit parameters, any advanced cutting parameters, and then pick generate. So we've generated a pocketing operation to program the pocket from the top face. In the next step, we will go ahead and drill these holes in here. I'm going to go ahead and analyze the diameter of the hole. So these are 3/8 inch holes. So I'm going to use holes and drilling, and I'll select holes on a flat area, and I'll pick the face right here. We'll pick a tool for it. So I don't have a 3/8 inch drill bit, so I'm going to go ahead and create a new one in here in the list. We'll go ahead and add a 3/8 inch drill. Specify a name for the tool. Save this up. And for the drilling operation, I'm going to go ahead and specify the depth in here, so I can just go halfway through since the part has a counterbore on the bottom side, so I don't need to drill all the way through from one side if the tool is not long enough. So I'm going to measure this distance in here, and I could say I only want to go slightly past the midpoint. I can say 1.05, and then specify a sorting sequence, and then generate it. So I'm just going to go past the midpoint or halfway point for the drilling operation in here. Finally, I'm going to add a chamfer toolpath in here for this edge. So use 2-axis chamfering. We'll select curve edge regions, and I'm going to select a chain of these edges around the part. We'll pick a tool for chamfering, specify feeds and speeds, clearance. So the workflow is very similar to how you've been used to programming your 2-axis or 2.5-axis toolpaths. You choose your cut start side, specify entry and exit, and generate. So now that we have programmed these toolpaths in here, I'm going to go ahead and run a verification, select simulate. So that gives the cut material simulation. So we have the toolpath simulated for the top. Now that we have programmed the top, we would like to go ahead and use the rotary axis to rotate the table so we could mill from one of these orientations. To do that, you would go under setup, the group under setup in the program tab, and pick rotate table setup. And now we can specify the table rotation angle. So based on the origin and the rotation center, you will notice that it automatically establishes the origin for the new orientation. So you don't have to go back and establish a new zero. That's the beauty of using 4-axis machining, is once you zero it out, you no longer have to go back and reset zeros for each orientation that you're machining from. So now that the Z-axis is normal to this face, we have inserted a rotate table setup in here. We could now program machining operations from this face. So I'm going to go ahead and start by creating a drill operation for these holes. I can analyze the size, the diameter of the hole in here to determine what size cutter I would need. That's a 1/2 inch hole. So I'm going to go ahead and create a hole machining drilling and select holes on a flat area, and I'm going to pick this face so it automatically picks the holes on each of the face right here. We'll pick a tool for it. We'll use a 1/2 inch drill. We'll set the feeds and speeds. You'll notice that the clearance plane is now automatically oriented parallel to your rotated XY plane. So the clearance is normal, and any measurements that you take for picking the depth are always oriented along the rotated plane. So I can pick the depth in here, and I can split the difference like what I did for the previous example. So I'm going to go half the distance in here, 1.5 inch deep. I can change this from a standard drill to a deep drill since it's all about 3 times the diameter of the tool. Specify your step increment. and you can apply your sorting sequence and generate the toolpaths. So if you've generated a drilling operation here, like a deep drill, in the next step, I'm going to use an end mill to go ahead and profile the counterboring here. So use 2-axis. I'm going to use hole profiling. We'll select the holes on the flat area right here. We'll pick the same 1/2 inch cutter. We'll specify the depth by selecting these 2 points. It's a 1/4 inch deep. You can specify the parameters for your hole profiling, and then generate creates your hole profiling toolpath. So now that we have program setup 2, we can go ahead and run a verification here. So you can see that the simulation from the first setup still remains as you're simulating the second setup. And since I haven't applied a sorting sequence, it was picking up in the order in which the curves were added. I can go back to the hole profiling and apply a sorting sequence and then run the simulation for it again. So now that we've programmed the 2 sides, we can go back and repeat the same for the next side here. So we would insert a rotate table setup. We specify the table rotation angle. Now these angles, what we are specifying here, are in absolute rotation. So we want to go from 90 to 180. And you'll notice that when you accept this, it automatically orients your coordinate system for machining to the bottom side, and your 0 is set to the top of the workpiece in the southwest corner. So I can now repeat one of the drilling operations in here. To drill to it, I can make a copy of this operation, paste it below, edit the operation. So you can copy operations from one setup to the next. You specify the regions, and then you specify the depth, generate the toolpath. I'm going to repeat the hole profiling operation in here for this face, selecting holes on this flat area. I'm going to pick a tool and then generate the toolpath. Now finally, we want to do the side 4, which would be a rotation of 270 degrees. So you could basically go back into the setup. You can even copy and paste the setups in here. I'm going to copy setup 2 and then paste it below setup number 3. And I will change the orientation from 90 to 270. And we'll repeat the operations for setup 4. So what you're seeing here in this particular example is we are programming the part from 4 different orientations using rotary axis with the help of rotate table setups. So now that we have all the sites programmed, I'm going to right click and say simulate all. So we're going to simulate through all of the setups. So now the part has been programmed from all 4 orientations, as you can see it. So this is using indexed 4-axis with a combination of 2.5-axis operations. Now, once these operations are programmed, you can post-process all of these into your posted output file by selecting the machining job, right-click, and choose Post All. And you can specify your output file destination location. Automatically, the file name is used for the posted file name. Your file extension is set, and selecting Post creates your posted output file. So you will notice that in your output, you see the initial A is at 0 degrees as you're programming from the top. And then we can do a search for the next angle in here. As you can see, you will see an A of minus 90 degrees as it orients to the one of the side faces. And you can also see the setup 3 that basically goes to A 180, and then finally A 270 for the final orientation. So folks, if you do have any questions, please feel free to post those questions in the questions panel. The next thing we're going to be covering is how we can use 3-axis operations as part of our index setup programming. Now to demonstrate this, I'm going to be go ahead and bringing in another example. Okay, so here I have a section of a piece of a table leg that I would like to program. And in this particular example, I'm going to be doing 2 things. One, I'll be using the rotation axis to be oriented along the y-axis, as some CNC machines or CNC routers could have the rotational axis oriented along the y. The previous example we used along the x, and we'll talk about how we can use some of our 3-axis methods in index setups. So the workflow would be very similar to what we talked about. So the first step is you go into your machine setup to make sure that you define your number of axes to 4, your configuration to table. And in this particular example, I'm going to be orienting the part is oriented along the y-axis, as the axis of rotation on the machine is the part rotates on the y. So I would pick the rotary axis to be y. And also in this example, I'm going to be leaving the origin and the rotation center to the center of the block or the center of the workpiece in here, rather than putting it to one of the corners like we demonstrated in the previous example. In this example, I would be leaving it right at the center, so your rotation center and the origin stays at 0, 0, 0. So there's no offset between your work coordinate origin and the rotation center. They're right at 0, 0, 0. So once we've established this, the next step is to select your post processor. So you can select your post processor. In this particular case, I'm just going to go ahead and pick a different post. I'll just pick FANUC as the post processor in the list over here. And posted file extension into the NC. We'll go ahead and define our stock material. We'll do a box stock. You can see the length, width, and the height. So now, since the part is oriented along the y-axis, the width is a little over 16 inches. The length and the height, which is the distance on the x, and the z is 2 inches because it's a square block that's 2 by 2. So the next step is basically to program our toolpath. So we're going to start by using a roughing operation. We'll use our index technique. So in this case, we'll program a horizontal roughing, which most of you are familiar with programming in 3-axis setup. So we'll use 3-axis horizontal roughing. I'll go ahead and specify a tool for this. We'll use a 3/8 inch end mill for the roughing process. Set the feeds and speeds, set the clearance, specify the cutting parameters, very similar to how you program on a 3-axis setup. And over in the cut levels, since we are programming this on a rotary axis and you have undercuts that needs to be machined from multiple orientations, I'm going to limit the bottom containment to just to go below the center line, just slightly below 0. So I'm going to say go past 0 by maybe 100 thousandths, so that when you rough it from the two sides, it doesn't leave any seam and overlaps nicely. And then you can control your engage and retract parameters, set any advanced cut parameters, and then pick generate. So with the index machining, the table rotates the part to the desired orientation that you specify and then stays locked as you perform a 2-axis or a 3-axis machining. So we've just programmed the horizontal roughing from the top side. We will go ahead and introduce the rotate table setup. And in this particular example, I'm going to rotate this to 180 degrees. You'll notice that the coordinate system triad rotates by 180 degrees. I'm going to click OK to accept it. Now I'm going to hide the world coordinate system display, so it just makes it easier for you folks to view the coordinate system. For the setup 1, the Z is normal to the top. For the setup 2, since we rotated it, it's going to be rotating the part on your rotary table by 180 degrees. I will repeat the same roughing operation for the bottom as well, and then right click and regenerate. So the roughing operation has now been programmed for the top as well as for the bottom. So the roughing for the top and the bottom. So I'm going to just rotate the view back to the orientation for the top, and we'll go ahead and run a verification. So we'll select the machining job, right click and pick simulate all. So you can notice that the roughing operation for the top and from the bottom side have been programmed. So you could be programming roughing from multiple orientations. In this particular example, I've just used top and the bottom. We will be covering continuous methods momentarily. So this is how you could program indexed operations using a combination of 2 and 3-axis operations depending on the type of features you have on the part that you'd like to mill. The next thing I'm going to be covering is continuous 4-axis methods. And for this, I will be starting out with our wrap methods first. That is going to be using wrap methods or using facing, pocketing, and profiling. Now, these wrap methods are available in 4-axis, expert, and higher configurations. And these are methods where can be used where parts have a constant radius, like wrapping, and does a unwrap and a wrap. The tool path is computed and wrapped onto a cylinder. So you need to make sure that these methods can be used on parts that have a constant radius. So we have different types of wrap methods that are available. We have facing, which is similar to your 2-axis facing, pocketing, and profiling. And I'll try to cover all 3 methods in this webinar today. So the workflow would be very similar. You establish your machine type, the number of axes, configuration, set it to table, specify the axis of rotation, and make sure the rotation center is set correctly. Now, in this particular example, you'll notice that the rotation center is being set to the center of the cylinder block, and I'm going to leave the origin also at the same location. So, on some machines, you will have to probably set it right at the center because they may not be able to handle the offset between the rotation center and the location of the origin. Most machines would be able to handle an offset. You could put the origin to the top edge of the cylindrical blank, and you could put the rotation center to be at the center of the workpiece. So now that we have established the machine tool setup, in the next step, we have the stock defined in here. So I'm going to go with a cylinder stock. Since we're going to be starting out with a cylindrical blank, we're going to pick a cylinder stock, and the stock can be defined by using cylinder stock, and you can specify the axis of about which the stock is defined. You can also specify the dimensions, the radius, and the length. If you need to make the stock larger than the actual finished part diameter, you can always change the radius, and you can also change the length of the stock in here. Now, we have some open pockets that you can see towards the end of the part in here. So these open pockets, we're going to be programming them using 2-axis and 4-axis facing operations. So using the wrap methods, we'll go to 4-axis machining, and we'll select facing. And the selection of your part regions, a curve region, would be very similar to how you've been used to doing it in 2-axis methods. You can either select a curve or you can pick a face edge. So in this particular example, I'm going to be selecting these face edges in here, the curves in here. Sorry, I apologize. So I'll pick a few of these in here for an example, so to save some time during the webinar. So I've selected 3 of these. Right click or press enter to accept the selections. In the next step, we'll pick a tool. I'll go with a 3/8 inch end mill, set feeds and speeds. And then you'll notice that when we go into 4-axis continuous toolpath methods, the clearance is represented as a cylindrical clearance, where you can specify the clearance to be automatic, a stock max plus a distance, or you could specify an absolute radial value here. So we'll just go with the automatic for this example. And then the parameters you could specify is the cut pattern, whether you want to do an island offset cuts or linear cut pattern, your cut directions, your step overs, and then your cut levels. So very similar to how you've used to doing in 2-axis setups. The same way it works in the 4-axis facing as well. And you can also control your entry and exit parameters. And then selecting generate creates your 4-axis tool paths in here. So it looks like the tool I picked is a little too big for the part I'm programming. So I'm going to switch it to a smaller size cutter and generate the tool paths in here. So we've now generated the 4-axis tool paths, 4-axis facing. So this basically unwraps and wraps it back. So this method can be used for parts that have a constant radius, like wrapping onto a cylinder. And let's go ahead and run a cut material simulation. So there's the simulation for 4-axis facing. So the 4-axis facing toolpath can be used for programming open pockets. Now we're going to use a 4-axis pocketing to program the pockets around the cylindrical face. We'll use 4-axis and pocketing. And these methods are available to you in expert configuration and up with the mill module. So I'm going to go ahead and pick these 4 pockets in here. So these could be curves, or it could be face edges that you could select for the 4-axis pocketing operation. Specify a tool, set your feeds and speeds. In the cutting pattern, you can choose the cut pattern. You can do linear, or you can do an offset pattern. I'm going to use linear with a cleanup pass. In the cut levels, we can specify the depth in here. I can pick the depth, or I could even measure it in here. So I can specify the depth and then pick generate to create the toolpath. So we'll now go ahead and run a verification. It automatically also determines the rapid transfers going from one to the other along the rotational axis at the clearance plane. Now finally, I'm going to go ahead and program a 4-axis profiling to finish these around the open pockets. We'll use 4-axis and profiling. Use curve edge regions. I'll pick these 3 curves around the open pocket. Select the tool, set feeds and speeds. So the workflow is very similar to how we're used to programming our 2-axis operations. I'm going to specify the cutting side to be the left of the curves. Cut levels is at the bottom. And then I'll leave the entry and exit as none, and then generate the toolpaths. So there's the 4-axis profiling toolpath. Now, post-processing would be very similar to how we did on the index setups. So you can highlight the entire setup, or you can go up to the machining job, right-click, and then choose Post All. Or you can specify the current post processor, and then select Post. So you'll now notice that your output has the 2 linear axes, your X and the Z, and then the A, which is basically the rotation in degrees. So this starts with your 4-axis facing operation, and is followed by the 4-axis pocketing operation. And finally, we have the 4-axis profiling operation. So the next topic we're going to be covering in today's webinar is going to be programming continuous 4-axis methods using our projection method. So we just talked about the wrap method. For the projection method, we will go back to the example that we programmed using 4-axis index roughing, where we did that, using the 3-axis methods, we did the horizontal roughing. So we'll use this example here, and we'll program a 4-axis continuous finishing toolpath for the leg section of the piece in here using a method called 4-axis parallel finishing. So this uses a projection method for 4-axis finishing. And again, you can find these under 4-axis methods, which is available in expert and higher configuration. So we'll go to 4-axis, and today we'll be covering 4-axis and parallel finishing. So we'll select 4-axis parallel finishing. Now, one thing to remember is once we program the indexed operations from the top and the bottom, we would want to go back and rotate the table back to the initial orientation. We'll put it back to 0. We'll accept that. So we'll add a new rotate table setup to rotate it back to 0 degrees, and then we'll go ahead and program a 4-axis continuous finishing method using 4-axis parallel finishing. So the 4-axis parallel finishing is a projection method where you can specify a containment region if you want to contain it to a certain area, but you do not have to select a containment region, and you can let it automatically compute based off the entire geometry, and we can use some of the parameters under cut axial containment, which I'll be talking about how to limit the toolpaths. So for this finishing operation, I'm going to be going and selecting a radius tool, like a ball mill tool. I'll pick a 1/4 inch ball mill tool for finishing. We'll set the feeds and speeds, and then the clearance. For all the continuous methods, you'd be able to specify the clearance is defined as a cylinder clearance, and you can set the clearance to be either a stock max, part max, or leave it at automatic, which is the default choice. In the cutting parameters, you could specify your in tall, out tall. If you'd like to leave any stock and you want to use this as a pre-finishing operation, you can specify a stock to leave. So for example, I could leave like 10 thousandths and then go back and finish it with another finishing operation to 0 stock. The cut patterns, there's 3 different types of cut patterns that are available for 4-axis parallel finishing. We have across, along, and helical. So in this particular example, I'm going to use along axis. So the cutter traverses along the length of the piece as it cuts, and then as it gets to the end, it basically steps, rotates your rotary table based on the step over increment that you put in. So by the time you go around 1 full revolution, you'll be able to finish the part. So from 0 to 360, you'll be able to get a finished part in here. So the cut parameters, you can choose your cut pattern, your cut direction. You can do zig or zigzag. So zigzag will basically cut both directions, traversing back and forth. You can also specify the cut axial containment. So if you want to skip these blocks, end blocks that you're using for supports from being machined, you can set the cut axial containment by setting the low and the high value. And each of these are represented by, graphically displayed using these planes in here. As you can see, I can set my cut axial containment. So in this particular case, I'm going to set it to 1.8 for the low value, and the high value also I'm going to move the plane so I can stop it, so that the total cutting area will be defined by the cut axial containment of the low and the high values in here. And then the start and end angle, 0 to 360, will basically do 1 full revolution to cut the entire part. We can also control the step over. I'll put in 15% for the step over, and then select generate to generate the 4-axis parallel finishing toolpath. So to program the 4-axis parallel finishing toolpath, you would need to have a solid surface or a mesh geometry. For the wrap methods, which uses curves, like using facing, pocketing, or profiling, you could be working with even just curves, or you could be working with solid surface geometries. But for the 4-axis parallel finishing in the projection method, you will need to have a solid surface, or you could even work with meshes like STL files for programming 4-axis continuous toolpaths. So now that we have programmed the 4-axis parallel finishing, I'm going to hit the play button to run the cut material simulation. So as you notice here, the cutter traverses along the length of the piece, and as it gets towards the end, it would rotate it by the increment angle. You can always speed up the simulation. And if you'd like to skip through the simulation at any time, you can use the pause to pause the simulation, and then select simulate to end to run through the simulation. So by the time it makes 1 full revolution, you'd have the part fully finished. So here we program a combination of indexed operation and a continuous operation using 4-axis parallel finishing. Now post-processing again, so you can just highlight the machining job, right click and use post all, and posting it will output the toolpaths in the order in which you have programmed. So you have the first setup in here, which basically takes care of the roughing from the top. The next setup, you'll see that it rotates it by 180 degrees for programming the roughing from the bottom. And finally, you're down to setup 3, where you start with the 4-axis parallel finishing. And you can see the continuous rotation with your Y and the Z, the 2 linear axes, and the A axis in here, which goes from 0, and it increments all the way from 0 to 360 based on how tight you specify the step over. It determines the angle automatically. So it goes from 0 to 360 degrees. Now, if your machine expects the rotation axis code to be a B or a W, this information can be set in the post processor to match the machine's rotary axis code.
A couple of notes on this part that Uday just programmed and showed you. One of the things that I would have done slightly differently here would be go across the axis, because when you're running the tool along the feature, you might get some artifacts. So I think the finished surface finish would be better if you go across the axis. Having said that, the other thing that Uday showed was the combination of both indexed and continuous finishing. So what I would like to say is, when you are removing material, large amounts of material, like in roughing or even in pre-finishing, if you're leaving stock and you're removing material, it would be preferable to use the index machining methods, because you're locking the table, and that would give you more rigidity in the machine. And so as far as the machining characteristics are concerned, it would be better to do it that way. And then finally, when you're near net shape is when you would really want to use some of these continuous or simultaneous finishing methods to view the final finish. So just a thing, just something to keep a note of. It's really more goes towards machining strategy. Thank you, Uday.
Thank you, Joe. So switch between the cut patterns. You could always go back, edit the operation, and you can change from along to across or helix, depending on what type of finish you'd like to expect. So you could always go back and change this and then regenerate the toolpath. Now, one of the other continuous methods that we would be covering today is going to be 4-axis and 4-axis engraving. So for this particular part, I'm going to go back to the example that we used earlier in the webinar today, where we covered on the cylindrical part, where we covered facing, pocketing, and profiling. I would be covering the 4-axis engraving, which is part of our projection methods in here. In this particular example, you will notice that the text that I would like to engrave has already been projected to the geometry using the CAD tools that are available in Rhino. So since I'm demoing this in RhinoCam, you can use the project command to project it to the surface. Now, once the curves are projected, or if the curves aren't even projected, you can project it using the 4-axis engraving methods. But in here, since they're already projected, I'm going to go into the 4-axis methods and use engraving. So for engraving, you can select curves, or you can even select surface boundaries, or even face edges as your part region for machining. So I have these 4, the letters and the text selected in here. The geometry selected for engraving. I could specify a tool for this. I could use a end mill, a ball mill, or even an engraving tool. So I could use a 30-degree engraver. Set the feeds and speeds, set the clearance, and in the cutting parameters, you could specify the total depth for 4-axis engraving. I'm going to put in a depth of 50 thousandths, and I will step it in, cut it in 2 steps. And then generating the toolpath will create the 4-axis engraving, and also you can see the transfers are being done along the axis of rotation. So now we'll go ahead and run a simulation in here for the 4-axis engraving. So you can see that my cutter was too big and the depth was also too large for this part. I could always go back and make necessary changes in here and then regenerate the toolpath. So that would be a 4-axis engraving toolpath. Now you could select curves, you could select surface edges, any type of geometry that you'd like to use on a 4-axis engraving. Again, once you have all of these operations programmed, you can post-process all of them out to the machine as one setup, or you can individually output them. So if you just wanted to post the engraving, right click and post. You could post the engraving operation out to your machine tool. And there's your posted output where you see your X, Z axis and the rotation axis in degrees. So with this, I would like to conclude my part of the demonstration for introduction to 4-axis machining, and I would like to hand this back to Joe.
There's a couple of questions today. One of the things that a couple of our webinar attendees wanted to see was how would you machine across the axes? You know, in the previous part that you had the indexed as well as the finishing methods. Can you bring that up and show how we would machine across?
Sure. So for the 4-axis continuous, I would change the cut pattern from along to across. And then if you need to change the step over, you can change the step over, pick generate. So this is going to basically go across. So you're basically going from 0 to 360 and 360 back to 0 as you make each pass and you step over from one pass to the next. So the across cut pattern would take a little bit longer time to generate compared to the along axis cut pattern. So as you can see, the toolpath is being generated. And once the toolpath is generated, you'll see the result of the toolpath in a moment.
As well as, I mean, not just generation on the machine here, but also on your machine tool as well, because you're spinning the axes constantly when you're doing that. While the along, you can think of it as locking the axes, running the tool, and then turning the axes, rotary axis, and then locking it again and running it again. So that's much quicker, but you might not get the finish that you want. Today, the other question that people wanted to know is how do we set up the extents along the axis? So they want to machine the actual cylindrical portion that's sticking out from that square block at the ends.
Okay.
So you can show how we can set the extents. Yeah.
Yeah. So just to save some time in this webinar, I'm going to go ahead and just pull in the same example. I have another copy here, so let me go ahead and do that.
So this is Uday's wizardry with multiple sessions. You can see that in action.
Yeah, so just to save everybody some time, I have this part in a completed fashion here, so I'll go ahead and pull the same example. So as we go into the 4-axis parallel finishing, if you go under cut parameters, you'll find controls for cut axial containment. So now the cut axial containment, as you look at it from the top view, you have your low and the high value. So the low value is the distance that you're starting from the origin where your rotation axis origin is defined. So in this case, I've set it to 1.75 inch and 3/4. So if you use even the measurement tools in your CAD, if I go to analyze and a point, if I measure this point here, that's about 1.789. So that's distance from the origin. So that's the low values where you're starting it from. And then how far out you want to cut it, you'll see this, the two planes, the red is the start and the green is the finish. So that's going to be 14.82. So this is along the length, the rotational axis. Now, if I want to keep it short, I can always change these numbers. I could say put in as 5, and then I'll just change this to 10. So you'll see that we are only going to be cutting within this stretch of this section here. So that's how you can contain your cut axial containment. Now, when I generate it, you will notice that the toolpath just stays within this section. So if you want to do some finer finishing, go back and refinish certain areas, you can actually use this. This is a great way to just restrict it to a certain area. You can also do the cut axial containment for angle. So if you don't want to do the entire 360 and you only want to go like halfway, I can say go from -90 to +90. So we're only cutting like just one half section on the rotational axis. So the cut axial containment will help you restrict and contain the toolpaths by specifying the low and the high value as well as the start and the end angles. I hope this helps.
Yeah, that's good, Uday. Thanks a lot. Do you want to see if that thing is completed?
Yes, it is. So,
yes, okay. All right, so
that's the across axis. And as we run the simulation here, you will notice that you're making complete 360 rotations for each cut. As you step over, you're going from 0 to 360, 360 back to 0. Since I've set it to zigzag, if you choose zig, it basically goes from 0, 360, 360, 720. So it basically keeps incrementing. So in this case, we are cutting back and forth in a cross pattern.